So we will have first lecture. The title is a reform framework to develop computational and statistical thinking. Presenters is Professor Isoda Masami, project overseers from University of Tsukuba, Japan, and Professor Araya Roberto, project overseer of InSight from University of Chile, and Dr. Sofian Azumi from project overseer from Malaysia, and Dr. Gonzalez Olan from Thailand.
Good morning, everyone. I'm Roberto Araya from University of Chile, Institute of Education. So we're going to talk about computational thinking for all. APEC, we have agreed that after reviewing the literature in the last decades, that have three pillars. One is algorithmic thinking, means following rules and being able to write rules so others could follow them. Must be very precise rules. Second is computational modeling. Build models of nature assuming that everything is digital, like a chessboard like here. So everything is very precise and there are movements in these boards. And third is machine learning. Machine learning is really booming last years. It's a mix between math and statistics, and it's a way to look at patterns. You don't, in this case, write rules to the computer. You just train the computer. The same way you train a dog, you train a cat, you also train the computer with several animals. So we're going to see in the three pillars different examples of activity to do computational thinking for all. First, an activity for algorithmic thinking for kindergartens, a basic model of coronavirus, how it is spread. Second, a computational model more sophisticated for primary school and middle school for coronavirus using a computational thinking in a board. And third, machine learning models, one for detecting patterns of who is going to be really ill and who is not going to be really ill. These are the three pillars. So we're going to do now first activity for kindergarten, first grade, algorithmic thinking. We're going to follow rules. We represent whole population, every person as a ball, as here. And we're going to have to follow the rule as a computer would have to do. At each moment, paint red every ball that touches a red ball on Ant's table. A red ball, like here, means someone is infected. So this is the first moment this is infected. Next moment, we are here. So we have this one that is red already because it's infected, and the new infected. We have again these two infected, and who else? Nobody else, because nobody touches them. So we can see here the first very simple model of propagation of infection. So now we have another case, that's Tom's table. So let's say here we have someone infected initially. Next day, you have this guy infected plus the two ones that touches them. So you are doing a cycle. And now we have to apply, who else? You see this one is going to be infected. And then next day, they're already infected, so you're following these rules. This is the code. You are doing as a computer. So the next one, they just touch, okay. And then nobody else next day will stay the same because they're not touching them. So this is a computational model of coronavirus disease. Here are two persons. This is infected, this is not. But one important effect is mask. You know, if you have a mask, then you don't have to be 2 meters away in order not to infect. It's like having a smaller ball. So without mask like this, with a mask like this, so we're going to see when there is a collision, they touch, they will get infected. Another important effect is the number of people, I mean the density. See, a lot of people there are very agglomerations. It could be, could be spreading the infection. With smaller one, less possibility of collision, but a lot of agglomeration, a lot of density, you have more possibility of the disease spread. So this is a computational model. And the other effect is motion. If everybody moves a lot, more possibility of collision, more collisions. See? So we have three effects here. Mask or not mask, density of population, and the motion, the mobility of the population. So now we're going to do the activity of machine learning. So we want to see a pattern of people that are severely ill, with COVID and those who not. So we have different patients here, people. For example, this is a lady, 79 years old, and not ill. But here we have another lady, 80 years old, she is ill. What is the pattern? Some of them are severely ill, means they are red here, and those not. We want to try to find the pattern. So machine learning does the following thing. First, select a training set, means some of them. Let's say this, and this. Okay, so this is going to be our training set, and this is going to be for testing. So here we are. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, and let's see, and here's another one, and here's another one. Okay, so let's see who is ill here. And here's 85 years old, and she's ill. So here's another one of this training set, and he's not. He's 27. He's around here. Here is another one, 66 lady, and she's ill. I'm gonna put it. This is ill. This is ill. I'm gonna put it here. This is not ill. Then 58, and he's ill. 58. Then 16, not ill. 16. Then we have 10 years old. Is nothing. 10, not ill. 68 is ill. So here, and then we have 20 is not ill. Then 70 is here. Okay. So can we see a pattern? From this? Of this? See, what we see is here are the red ones, here are the white ones. So what? He's 50 years old, 40 years old, 30 years old. So maybe you see, maybe it's around 50 is the threshold, but you have this case. Okay, so it's not completely absolute. So see this pattern, all the red ones are there except this. Now this is a testing set. See, now here comes a lady of 80 years old. So according to this pattern, she should be ill. Is that right? Yes. Okay. So this is okay. So and we could test all these other ones as well. So we have built a border with this training set, and the training set says, look, the thresholds are around 45, 50, but there are some exceptions. So this is a machine learning way, and when you represent all the information of all the patients on the number line. Which one of these computational thinking pillars should we use? Well, that depends on the problem. So when you have a problem, you have to first think about the following. How much data do you have? You have not much data, or you have a lot of data to build the model. If you don't have much data, then you have to rely on some type of knowledge from experts. And there are two kinds of knowledge, just heuristics, a lot of experience, and then you write rules, and these algorithms basically sync rules and programs with cycles. If you have scientific theories, like nature is made with particles, people are agents, it's like little balls, then you do a computational model. Now, if you have a lot of data, then you go to machine learning. And there are two cases. One, when the data is already labeled, for example, in the people already sick or not sick. So then you use supervised machine learning. So they tell the machine, all these patients, and these were really severely ill, and these were not severely ill. If you don't have that, then you have to look for patterns. And this is unsupervised machine learning. Hope to see soon in Tsukuba and Tokyo. Thinking is fun.